Maybe this is my first time to give the public meeting talk, so I have come here for 2 years, almost 2 years. So I'm very lucky to be on this position for the first time that the introduction of the quantum computing. Yeah. So my basically my research topic is on the quantum algorithm. But recently that the topic of quantum error correction is very hot in the quantum computing. And also very fast developed in recent years. And maybe today I will talk about this specific this called bit flip code, and to show you how the
By the way, for visitors, so no questions during talks.
yeah, we can have after the talk. I will expand briefly on how the error correction works, and maybe we can hope for more collaborations in this topic. Okay, so today the title of my talk is the God saves quantum computers by playing chess. So this you know that in this title is inspired from QEC sonnet by Daniel Goldsman, which says we simply measure it, then God plays chess, typing it into X, Y, or Z. So this collapse means quantum collapse. That when you perform the measurement, a quantum state will collapse. And but now it is not a collapse of quantum state, but the collapse of some operator. This X, Y, or Z, you can simply imagine it as a matrix, linear algebra matrix, only matrix. So this is the 2x2 matrix of X and Y, X and Z. We will only use these two matrices today. Okay, so before talking about quantum computing, this is the quantum circuit. I briefly introduced some basics about the quantum mechanics. So the first concept is the qubit. The qubit is a two-dimensional vector, and people usually imagine it in a sphere, where this vector has two complex number, alpha and beta, which we call it amplitude. The alpha and beta satisfies this normalization condition, ensuring that this quantum state is normalized. And by drawing it on this block sphere, we see that it is nothing but a spin up and spin down, and which is just like the fermion has the spin up and spin down. And if we the quantum noise will be so because this alpha and beta is a continuous number. Maybe it is 0 and 1 in the if you consider a classical bit, just a classical bit, it is just a absolutely 0 or 1. But in the quantum mechanics, problem of quantum states and quantum computing. So and also the quantum error correction is proposed to correct this error without knowing A and B. Okay, so this is the motivation. about quantum error correction. Okay, so the second concept is quantum gate. I only this is the CNOT gate denoted by this symbol. To know the function of CNOT gate, we only need to know how it acts on some initial state. For example, if the initial state is 0, 0, it will keep the state unchanged, still 0, 0. But if the first qubit is 1, then it will, and the second is 0, then it will just flip this second qubit, and such the final state is 1, 1. This is CNOT gate. And the third is a measurement operation in quantum mechanics. So the measurement operation in quantum mechanics is very subjective, which means we need to choose an observable. For example, the observable is this diagonal matrix, two-by-two matrix. It is 1 and -1. And the measurement result is the eigenvalue of this observable, which is just the +1 and -1. And after the measurement, the quantum state will be collapsed, which is this collapsing. And the collapse will be mathematically be described by this projector, which is 1 + O/2. So this is determined by the eigenvalue. Actually, there is an eigenvalue here. So we need to choose the projector according to the measurement results. For example, this projector is just a 1 + 1 - 1, and which over 2, which is 1, 0. So this is a projector of 0 state. This is a projector. So this will collapse this quantum state to the alpha 0. So this alpha, if we square it, the pre-coefficient denotes the probability of deriving the this quantum state. Also, this beta is just square it, and it is a probability. Okay, so this is a measurement process, and finally, this is some basic mathematical property of polymetrics. The first is the anti-commutation relation of z and x operator. That you can check that this zx equals to -xz. This is some just a simple linear algebra and fact. And the second is the x squared is identity, which means nothing happens. And the third is that this z operator applied on the if consider two qubit poly operator, z applied on 0, 0 remains 0, 0 unchanged, and z applied on 1, 1 also remains this 1, 1 unchanged, because z applied on 1 is just 1 - 1 applied on 1, 0, and keep a minus sign of 0, 1. But if this minus sign is squared by the two qubit results, so this minus sign is still identity. So this also makes this 1, 1 state unchanged. So this is the basic effect of the mechanics that I will use today. Okay, so now let's look at what happens in this whole quantum circuit. It includes 5 basic steps, including the decoding. The error happens. Then we have to detect the error, the detection, and the decoding process to find what exactly the error is. And then we perform the correction by some gates. So we start from the first. That's initially we have this quantum state of alpha 0 and plus and beta 1, which is a single qubit state that we want to protect from the error. Then we apply the CNOT gate to here. You can see that this 0 and 0 correspond to this 0, 0, and remain this state unchanged. But this 1, 0 will flip the resulting state. So which means that this is two action of CNOT gate, but it can also be the superposition of these two operation, which is alpha and beta in the amplitude of alpha and beta. So this makes the final quantum state here to be the alpha 0, 0 plus beta 1, 1. Okay, this 1, 1 and 0, 0. yeah, this is the first CNOT gate. And and similarly for the second CNOT gate, we denote this quantum state to be we denote it to be psi e small e. It is naturally to be the triple duplication of this quantum state. That's 0, 0, 0 and 1, 1 state. Okay, so this is the encoding process, and we just simply make the information redundant, and then an error happens. So now the error is happened around across the all the 3 qubits, and this is denoted by the some also have some coefficient A, B, C, D. It is more complicated than this single qubit noise because we introduced 3 qubits now. And all of this alpha, beta, A, B, C, D are ongoing. And we have to correct this error without knowing how large this coefficient is. Okay, now next step is the detection operation. Then we can denote this one. And the state after this is denoted by this E applied on the psi E state. Okay, so then we perform the detection operation using this quantum circuit. So you can see that there are two operator product here, which is the Z1, Z2, and we can write it. This is the tensor product of two matrices, such that the tensor product of 1 minus 1 tensor product of 1 minus 1, which is equal to 1 minus 1 minus 1 1. Yeah, so so here we have the observable and of 1 and minus 1. Here the observable is to be a 2 qubit observable. So 1 minus 1, 1 minus 1, and plus 1. And in the language of quantum computation, this measurement process is called Hanma test because we use some 2 Hanma gates here and perform the measurement on this ancillary qubit. So this measurement result corresponds to measuring this expectation. So we don't perform the measurement directly on the qubit because it will destroy the qubit. Instead, we perform the kind of indirect measurements on the ancillary qubit, and we just measure this product of Pauli matrix. So we can see what is the result after this measurement. So it have two observable measure here. So this corresponds to the Z1, Z2, and this one corresponds to Z2, Z3. So and it will measure what measures is the eigenvalue, eigenvalue of the operator, including +1 and -1. Okay, I will write a chart on what the measurement result is. Z1, Z2, Z2, Z3. +1, +1, +1, -1, -1, +1, -1. Yeah, because both observable only has 2 eigenvalues, so there are only 4 kind of these combinations. So so we will use this projector to see what is the quantum state after this measurement. I will let me for some calculation over here. Okay, for example, if what we measure is this +1 and +1, we will have a projector of 1 plus Z1, Z2 over 2, 1 plus Z2, Z3 over 2. And the arrow is A, I, E, X1, D2, D3. And this is the arrow. And we apply on the encoded quantum state psi e. So to see what's its effect, we only need to perform some commutation. We want, for example, we want to move this projector through this arrow. And for example, we commute this operator with, for example, this ZX2. We will see what the effect of this identity. Z2, Z3 over 2. And C is a C number. And now precisely. And notice that here we use the anti-commutation relation between this Z2 and X2. But this identity keeps this X2 invariant, such that the result is X2 minus identity minus the 3 over rather than direct the states part of that's one. And this minus sign appears because of this anti-commutation relation where the minus sign comes over here. And then the identity applied on the initial state makes the state unchanged. But also this Z2, Z3 applied on both 0, 0 and 1, 1 makes the state unchanged. So this is important because for the quantum error correction. This Z2, Z3 is usually called the stabilizer of the encoded quantum state, which ensures that its application on the state invariance, and also because these two simple mathematical relationship according to the linear algebra. So this is unchanged. So this is simply that we have this state minus this state. That's the psi e minus psi e over 2, and which is 0, which is vanishing. So this is surprising. The arrow is vanishing after the measurement. So only you can see that using the similar calculation, we find that after the projection, only all of the arrow is vanished if we measure the 1, 1 projector. So the only result is the A identity psi e, which is the psi e itself. So after the measurement, no error happens, nothing happens in graph. So we only leave amplitude A, means that the probability of measuring of getting the plus result is A squared, which is the probability. So so we can denote the result here A psi e. And also if we measure the results of +1 and -1, we will find that there will be a minus sign here. Yeah, if you remember the previous calculation, the result is just keep this quantum state unchanged, and the result will be a minus b x3 psi e. So we will see that there will only be a very simple x3 noise, x3 arrow, and the corresponding amplitude is p squared, is the probability of deriving this x3 arrow. So this is so the corresponding state is a bx3 value. And similarly, we will find that all the results correspond to some discrete arrow. For example, this is bx1 psi e. and this corresponds to CX2 value. So we will see that after the measurement, the noise, the collapse, the noise is collapsed, and it's collapsed into the discrete identity x1, x2, x3. So this is how the gun place dies by some with some probability, but it saves quantum computers because we have very discrete operation of this quantum noise. We don't this A, B, C, D disappears, but only converted to some probability of the collapse of the measurement results. Okay, so to correct this there are still some errors of x3, x1, x2. To correct this error, we need some classical calculation, which means after this measurement results, we should design some digital quantum circuit, classical digital circuits, including this NOT gate. This is the symbol of NOT gate. For example, if the result is +1 and -1, which corresponds to this true line and the false line, and we want to correct the apply x3 gate here. So we simply connect this true line here. We can know we should have the connection here, and the false line comes here. So according to this measurement results. And for the second row, because the arrow is x1, we connect this. We have applied this one, and we have this -1 minus here. So we connect this false to this AND gate, and the true gate and the true line is connected to here. And finally, the -1 is two false gates. So we just have a purification of the classical circuit. And we can design a corresponding classical circuit to correct the error. So this is completely classical. So we can see a very distinction between the quantum circuit and classical circuit. For the classical circuit, it has this purification operation. You can just copy a classical state. You can have a branch of the circuit. But in quantum circuit, it is impossible. You cannot have a quantum circuit just like this. Because of the non-following theorem. This is the one of the basic theorem of quantum mechanics. But the classical circuit is much more convenient to have this duplication. Okay, so after this correction, we apply this x1, x2, x3 to this error, to this incorrect state, such that because we have x squared is identity, so we just apply it x3 twice to make this state unchanged. So no matter what the error collapses to here, after the correction, we will always derive a final quantum state of psi here. It encoded quantum state. So the error is disappeared. So this is how the quantum error correction is worked in the quantum circuit. So this is I extend how this quantum error correction works. But in reality, in practice, or in the frontier of quantum computation, there are much more problems to be solved. For example, we can ask why the error happens here, right? It happens here, here, and here, everywhere. Also, ancillary qubit has error. So, what if the error happens here? Yeah, it will make things more complicated. And also, you can see that this classical computation is we can design such a classical circuit because we only have two ancillary qubits. And we can have this chart of only 4 cases because we have 2, which is equals to 2 to the n. In the practical quantum computation, the number of ancillary qubits would be, for example, 50. So we will need to have a chart of 2 to the of this 2 to the 50 number of possibilities. And this is equals to around 10 to the 15th possibility. So you cannot even write this chart, right? So in practice, we need to dynamically to calculate to determine what the error is. So this is where the classical computer come into play as an important role, where we will usually need this FPGA or GPU or machine learning to performing this decoding process. So yeah, also you know that some news says that the NVIDIA is going to come into play the quantum computer in the decoding process because they have very fast GPU to make this process fast. We need to keep this fast because you can see that the quantum states have to wait the classical computation of this circuit. So the quantum state will be disappear during the process. We have to make it as fast as possible such that the error rate is controlled. So there are many unsolved problems in this quantum error question, and I hope you can derive some message after in my talk. Thank you.
So have very accept questions from non-experts. Yeah.
Thank you very much for that talk. So you assume that this error is written in that form, the linear combination of those x's.
Yes.
But in general, this can be arbitrary unitaries.
Yeah.
And in those general cases, how would you treat with those errors?
Yeah, that's a very good question. That for example, in general, the quantum operation, you can assuming that this operation is just a unitary operation, for example. And usually the unitary operation can be, for example, the single qubit unitary operation can be decomposed as A, I, B, X, C, Y, B, Z. This is just a 4 bases of the single qubit operation. And the ABCD can be arbitrary coefficients. So using the similar idea that you can find that the corresponding quantum noise is collapsed into either X or Y or Z or Z after some proper measurement. Yeah, this is very good question. That you can prove that you can conceive some quantum code to measure to correct this discrete quantum noise. Yeah.
I'm sorry.
Oh.
So what type of object is this X1? Is it a matrix?
Yeah, matrix. X is just this one. Z. Yeah. So you for 2 by 2 matrix, you can always have some orthogonal basis to represent it. Yeah. Yeah. Y is 0 minus 0. So this is the 2 by 2 Pauli matrices, which form a basis of 2 by 2 speeds. Yeah.
Thanks for the talk. I thought one thing, could you help me understand the no cloning theorem a bit better? Because it feels like in the circuit, cloning is happening possibly in 2 places. The first is when you go from 0 to 000 or 111. It feels like that's like a replication code just in like classical error correction. So that feels a bit weird to me. And the other is, you said that you can't just like have a branch on the circuit. But aren't there branches at each of those Z2, Z1, Z3? Because they go right and down. So isn't that another, like, how does that not conflict with the no cloning theorem?
Okay. Regarding the first question, that actually this is not the cloning of quantum state.
Okay.
Yeah, this is the cloning quantum state means you start from a psi e, you come to the psi e tensor psi e. Which is you can have that some 0 0 0 0 0 1 1 0 1 1.
Okay.
So this is not this tensor product.
Okay, sure.
So you just
it's like lower dimensional.
Yeah. You
Okay,
just
nice.
put just some states. So these 2 states is completely different.
Okay, makes sense.
Yeah. And for the second question, you say this kind of operation is impossible. But this kind of operation, you mean?
Yeah. What's the difference between the 2?
Yeah, this is just a gate, just a matrix applied on this.
Okay.
Quantum
But
state.
there's like 2 parts that are going out of it. So doesn't the result have to go in 2 different parts? Like if you put an I there instead of a Z, how does that not just become a trivial branch?
Trivial branch.
Like the one that you said was impossible down to the right a little bit.
Yeah, for example, in this operation,
Mhm.
you apply a gate to it, but you didn't clone it. This is just from 0 plus 1 to 0 0 plus 1 1. That's like this state. So
Okay.
the resulting state is just a replica of the basis, but not the replica of the state. So the non-cloning theorem stated that even if you have arbitrary unitary operation, you cannot make the
Okay. But then, so that does make sense, but then don't you have a clone going down and going right? Like you didn't clone the input, but the outputs are clones of each other. Or maybe I'm misunderstanding how the lines work.
How the lines work?
Like the part that goes down from Z3 and the part that goes right from Z3, are those the same number? And if they are, aren't those like clones of each other?
No, they are not the same.
Okay.
This is just a gate. You can imagine this gate as a hoop. So which applied on these two qubits. Just like this CNOT gate.
All right, sounds good. So I think I'm misunderstanding the basis order. So I'll have to look into that.
So we usually treat the qubit as horizontal, and the vertical is completely different things.
All right, thanks.
My question is about the error matrix. So why doesn't it have terms that have operators on multiple qubits at the same time?
That's a very good question.
Is that an assumption?
Yeah, this is assumption. Yeah, so in practice, we certainly we should consider a more complicated qubit, but this is out of the ability of this bit flip code. You should have more complicated. For example, you should introduce more qubit here. For example, the 5 qubit. If you have 5 qubits, you can correct maybe you can correct a 2 qubit error. So you can have errors like x1 and x2. But this you can imagine that this x1, x2, the error rate of x1, x2 is certainly smaller than x1 because x1 is more local, and such that the noise can have is more probability to have single qubit nodes. Yeah. So the error correction is only to correct the leading order error, but the higher order is not correctable.
So if you have an actual device, so depending on what device you have, the form may be actually different from each other.
Yeah, very different.
And you design the error correction method based on that knowledge.
Yeah. You have to assume that the larger weight error is have smaller probability.
A very naive question. This is the physics process actually applied inside the quantum computer.
Yeah.
Is there any evolution equation, time evolution equation motion? For example, I want to know how the purpose of this process is to stabilize the quantum information. And I want to know the lifetime of the information, because this improves the lifetime. Okay? So how to calculate the time scale without time evolution information? Corresponds.
Yeah. Time scale. I think this really may be related to the the previous question, that how large the error remains. Because even if we correct this error, there are still some higher order error happens x2, but it can happen with some smaller amplitude. For example, the B tensor C, the BABCD BCD, we assume they are small, and but there are still some higher order correction, higher order error that we cannot correct. So the corresponding lifetime that you ask, maybe it can be proportional to the B squared C squared over 1. So which means you just assume as kind of decay, and it will decay with some probability B squared and C squared. So that the lifetime of the error corrected quantum states depends on how powerful the error correction code is. So if it only correct a single qubit error, then the error will be this C squared P squared. If the error correction code can correct this error, but remains with some error of B, C, D, then it will be some B squared. So this makes the lifetime longer. So this is kind of a perturbation perturbation series. So if you have more qubits and correct larger weight error, you can have longer lifetime. Yeah, but regarding the equation of motion, I think because this kind of dynamics is highly time-dependent dynamics. So at different time, you will have a very different interaction. So you can imagine it as a time-dependent Hamiltonian evolution. And it is indeed very complicated, and there is no uniform Hamiltonian that can be described the whole process. Yeah.
Okay. So you assume that the error is will be happen after the coding, but I think what happens if the error inside the coding part happens inside the coding part?
That's a very good question. For example, we have arrow here. Yeah. So you can have there is a simple equation of CNOT gate. This X CNOT gate is equivalent to CNOT gate here, and then X. So you can prove that because this CNOT gate is a Clifford gate, so it is just arrow propagates from single qubit to two qubit. So this is nothing but also the previous problem that if we can correct this arrow instead, but apply a 2 qubit arrow or in this block. So this is we maybe need to introduce ancillary qubits, more encoding qubits to correct this 2 qubit arrow. So all the arrow actually can be gathered into this block by performing this kind of unitary operation. So this makes the story maybe simpler to consider. Only happens this block. Yeah.
Yes. More questions? So from anybody, including experts? Yes.
Also, is it the same arrow happen? I mean, where the same arrow happen when you use the analog quantum computer? I mean, here you use a chip.
Yeah. I know it's very hard to perform arrow correction, I think. Yeah, this kind of digital operation is much more is not very natural for that now. You have a very strong interaction between qubits. Yeah.
Yes.
Could you explain the title of your book?
Nice. Oh, nice. Nice is apparent. You play you because Einstein says that God never plays that, but actually God usually plays that when you perform measurement. So there will be a dice played when you perform measurement. It will give you either +1 or -1, and you should performing the error correction according to the played results. So this is where the God will plays a very important role to save the computer.
Yeah. Any questions? Yeah.
So how hopeful is it for us to get real practical computer?
That's a good question. I also want to know. Optimistically, I think maybe 5 years.
5 years.
Always 5 years.
You're much aggressive.
Any questions from online participants? So let me ask one question. You said that one of the difficulty of quantum error correction is all the decoding part. The scalability of this decoding part is a very big problem.
Yeah.
So what do you think the most difficulty, the current difficulty for future fault tolerant quantum computing? So that
there are maybe I think that in the hardware and also in the algorithm side there are also some difficulties. For example, in the hardware, you need to make this reaction as fast as possible, and you want to make the FPGA much close with the quantum chip. So this is difficult because the quantum chip is performed in very high low temperature. But FPGA is designed for the room temperature. So you have to integrate them in one very small place, and this makes the experimentalist very hard. And for the algorithm side, for example, actually, there are, even if you have some machine learning, you still have some possibility to have the wrong fraction. Because in this in the practical error correction code, there is no this 1-to-1 correspondence, but maybe many-to-1 or 1-to-many correspondence. So usually you will just take the wrong error correction and makes the results, the corrected results still wrong. So we want to make this 1-to-1 correspondence as accurate as possible in the algorithm side.
So in order to realize, for example, 100 logical qubits, how many physical qubits is necessary, and also where you need this the classical decoding part, and so what kind of
the scaling, for example, using the state-of-the-art surface code, it is not 50 but 1,000.
1,000
logical and zero. So both are 1,000. So this makes this possibility of the results to be totally 1,000.
Solution.
So you don't have to perform some dynamic calculation of the error.
Oh, I see. So these are so decoding part is the most difficult part.
The decoding and also how to design good enough code to protect it from higher order error is also very powerful.
And to my knowledge, well, so this is the gate consisting of only Clifford gates. But for non-Clifford type, well, is there still a theoretical issue unsolved? Or
I think the non-Clifford gate requires some how to apply the quantum gate and to the encoded quantum states, and there are still some magic state installation or the magic state cultivation, and to inject the T gate is into the high order gate. And this to apply this gate on the quantum computer, there is no theoretical limitation, but it is very time consuming. The time of applying this gate is around 10 times 1,000 times than the Clifford gate. So this is much time consuming in the quantum correction. But Clifford gate is much faster.
Okay, thank you. So no further questions.